In this video, I'm going to show you how to create equations to model exponential relationships. So suppose you were given a table and I asked you to figure out what kind of relationship this is, linear, quadratic, or exponential. So a quick reminder, linear, we need constant first differences. For quadratics, we need constant second differences. For exponentials, we need constant ratios. I'll show you what I mean by those in a moment. However, whenever you're trying to analyze this, x's have to have a consistent pattern. Looking at our table, we have 1, 3, 5, 6. So it breaks the pattern here. So if we remove the point 6 completely out, we can continue analyzing because then it's always up by 2 from all of the remaining points. Because if you do not remove this 0.6 and do differences with this a number that I crossed off, it's going to mess everything up for us. So let's start off by doing change. So this delta symbol is change in y, or the first difference. So we notice that all of these numbers don't end up being the same. So that implies it's not going to be linear. Then we're going to do a second difference, or a change of a change in y. And here, if we do the first two, it automatically also is not equivalent. So it's not a repeating number. So it's not a quadratic. A quick reminder how to find differences, if you've forgotten. What I'm doing is bottom subtract top. So for example, for the first difference, we had to take this bottom number, negative 0.5, subtract 2.2, and I got this negative 2.7. Or the one that's on the bottom of that one, we have negative 5.8, subtract the one above it, so negative 0.5, and that's the subtraction shown over here to get this negative 5.3. And with second differences, you do the same thing just on the difference numbers. Bottom minus top to get this one, this bottom minus this top to get that one. So because it's not linear or quadratic, we're going to figure out whether it's exponential. So for exponential, we're going to be looking at ratios. We're going to do bottom instead of subtract top, we're going to do divide by top. So this bottom one divided by that one over here, this division yields this number. Then the next pair, this bottom one divided by this one above it, gives us this. So the conclusion might be reached to say, oh, maybe this is not exponential. However, I want you to know that if an exponential has a shift up or down, the ratios that you will see on the y's or the outputs will not be consistent unless you remove that shift. So these ratios over here were done on the original y's. There was a reason why I kept this first difference column here and why I did them all. Because what we can do, if the original ratios don't work, please still check ratios on the first differences. So you can basically think of the differences that we have found here. They kind of eliminate that shift up and down, and now we can perform ratios of these differences. And so this bottom one divided by this top one is approximately this. This bottom one divided by that one is approximately that. It is not perfect because all of these numbers in the table were originally rounded anyways. So as long as it's pretty close, we could say it's an approximate exponential, and we're going to find an approximate model for this table. So to find this model, we're going to use the simplified version of an exponential with a single x as an exponent. So what we can do is we could substitute 3 points to find a, b, and c. I'm going to perform this for you. However, there are also some shortcuts. I'm going to write them down, and then we'll see as I find a, b, and c in the long way that the shortcuts will work as well. So instead of having a single x as an exponent, we can also say that this exponent will be x over some sort of number I called p. Sometimes I refer to it as period, that's why I called it p. And if you do end up going this way, then b is going to be the actual constant ratio we have found. So for us, approximately maybe 1.96. And the p is going to be the change in x's for this ratio b. So the change in x's for us is plus 2, plus 2, plus 2. So let's see what we can do with that. So I'm going to keep this information beside us as we go with this first option of finding a, b, and c using 3 points. So if this is the equation, we're going to plug in the very first point x1 and y2.2 into the equation, and then leave it because we have 3 unknowns, then plug in another point, point 3. So 3 goes in where x is, then negative 0.5 goes where y in the equation, and then again leave it for now. We have 3 unknowns. Substitute yet another point. We have 3 unknowns, a, b, and c to look for, so we need to plug in 3 points to be able to get 3 equations. So 5 goes in for the x, negative 5.8 goes in for the y. Now to work with 3 equations, 3 unknowns, we need to eliminate some of the variables. Let's call these equations 1, 2, and 3. Let's start by eliminating this plus c. Because all equations have this plus c, we can do some subtractions to eliminate that plus c. I'll do 2 subtract 1 over here. So 2, so this negative 0.5 subtract 2.2 will be this negative 2.7. Then ab to the 3 subtract ab. These are not like terms because the exponents don't match, so just leave them. And then c minus c is going to disappear. In this equation, we can call this equation, oops, I should have called it equation number 4. Let me fix that. So now this equation number 4 has only 2 unknowns, a and b. We would like to have another equation with just a's and b's. And so we will eliminate c from another pair. So 3 subtract 2. We can be doing that to eliminate the c's again. So this negative 5.8 minus negative 0.5 gives us negative 5.3. A, b to the 5, subtract a to the a, b to the 3. We cannot actually subtract them, so write them down side by side. They're unlike terms. And then c subtract c will disappear. And here we again factor this result. Why we're factoring? For us to be able to eliminate a or b with these 2 equations that we have here, if we didn't factor, we could look at this version of 4 and this version of 5. We don't have like terms to subtract here. We can't just say AB is like any of these. So subtraction is not going to work, but we can also try to eliminate by division. However, we cannot divide terms. We can only divide factors, and that's the reason why I was factoring here. So once you have the factored versions, what we're going to do is divide. It really doesn't matter how you divide, but I like to have higher exponents on the top. So I have equation 5 on the top and equation 4 on the bottom. So we have this negative 5.3 divided by negative 2.7. That's here. This numerator right here, and this is going to go in the denominator. And then we can simplify this. Because these brackets right here, or this factor itself, is identical to the one on the bottom, those divide out. A and A divides out, and b into b to the 3 becomes just b squared. And these divisions gives us 1.96. I hope you remember that this number we had as our common ratios before. So when you're trying to solve for the b, we're going to do square root of both sides. Usually I told students that when you square root, you have a positive and a negative. However, this b represents base of an exponential. In the previous video, we talked about the base of the exponential will never be a negative, so you don't have to do plus or minus here. So either actually work out the square root of this number or just leave it like that, or leave it like this 1/2 version. So next, I want to point out the shortcut. If you choose to use this other version, we wouldn't have had to plug in 3 points and do all of this algebra, because on the previous slide, we have found the constant ratio to be 1.96. So we could have said right away that b is going to be 1.96, except not just by itself, it's going to be also 1/2. So where does this 1/2 come from? So the 2 itself here is the ratio, sorry, not the ratio, the differences in x's. How did it jump from one x to the next? It always went up by 2 plus 2 plus 2. So this 2 right here is related to that. So if you're thinking of this x over some sort of numbers, it's like x over 2. That 2 comes from change in x's. Regardless, let's continue the long way. So if we found this b, let's continue on. You need to find the a, and then you have to find the c, and so on. So if once you found the b, we can plug this b into one of the equations that has only a's and b's. So you could choose 4, or you could choose 5. I chose this one. So all you're doing is replacing b with the number that we had here and simplifying as much as you can, and it's going to be an approximate number. -2 is not going to be exact because all of these numbers, again, I told you that they were rounded. Once you found the a, we have a and b now, we still need c. So now you go back to another equation that has a's, b's, and c's. So you could use either 3 or 2 or 1. 1 is the easiest to use, so I plugged in the a that we found, -2, the b that we found over here, and then work that out to be approximately 5. And now that we have all a, b, and c, we can rewrite our model by following the formula here. And so because we have to the power of x, so imagine this whole base was to the power of x, that's equivalent to saying just x over 2, which relates to back to what I was talking about over here. So if you really wanted to, you could leave it like that, or you could have done a square root on this base and actually said it's just 1.4. So here's the long way of finding a, b, and c. Let's do maybe another question that we can utilize this shortcut. Make our life easier. Oh, before we move on, don't forget, whenever you have your model, do a quick check whether it works or not. So take a random point, so take this last point for example, and plug it in for the x into our model, and plug in the y value on the left side, and then see if it actually matches up. It doesn't match up exactly for us because there's some rounding error, but it's close enough for our approximation. So let's try another. Here we have a table. We're going to do ratios of y. So this next one divided by the previous one, we got this. Then this next one, -58, divided by -22, we get this. And so on. Notice here, they're not close together. They keep just increasing like this. So maybe there is a shift that messes it up. So let's do the differences first. So find change in the y's. And notice, by the way, I forgot to mention, but x's do go up consistently, so we didn't have to fix anything but the points on the original table. So change in y now. So this next one, subtract the one that's previous. It's -12. This one, subtract that the one in front of it is this, and so on. Now that you have differences, try ratios on the differences. So this divided by that is +3. This divided by that is +3. And last by the previous is also 3. So it is actually exponential. And there is no rounding error here. It's exactly 3, 3, 3. So now let's use the shortcut. Instead of finding both a, b, and c using 3 points, 3 equations, which became really a headache, we can say that the base indeed is 3. And the p here, how long does it take for it to triple, is just up by 1 on the x's. So then this is x over 1. And now because we have only a and c still unknown, we just need to plug in 2 points and work with 2 equations, which is much simpler. So we're plugging the first point into the equation. So 1 goes for the x, -10 goes for the y. Plug in another point. So 2 goes for the x, -22 goes for the y. Label equation 1 and 2. Subtract them to eliminate the c's. So -22 subtract -10, be -12. This is 3 squared, that's 9 a's and 3 a's. So we can subtract like terms here. And c subtract c is just gone, so there's no c's here. So that gives us 6a equals negative 12, and then when you divide by 6, you get a is negative 2. The last thing left is to find the c. So you take a and plug it into one of the equations. I use this one. So a plugged in, negative 2 right here. Multiply with the 3 that's here, that's negative 6. Add 6 to both sides, you get your c value. And so the model for this equation is shown here. So hopefully that kind of shows you that you can eliminate some of your work if you find out your actual ratio, and then use the ratio as your base and the change in x's as your denominator in the exponent. And as before, verify that this actually works. I use the very last point, 5, negative 490, to check that it does actually work out. Let's try another one. What if you're given a graph? So if you're given a graph, there's even more shortcuts that you could take, especially if the graph itself shows you horizontal asymptote and shows you the y-intercept. Then this question is super easy. Watch this. So in this format over here, we can say that the last value here, plus c, is horizontal asymptote. And we know that in general for this format, y-intercept is going to be a plus c. How come? To find y-intercept, we plug in 0 for the x. So b to the 0 is just 1. So a times 1 is just a plus c. So I hope that makes sense to you. So why is this useful? Well, for us, we can see from the graph the c is 2. We can also see from the graph, if you count here, 2 squares is 1 basically. So you're going down, that's negative 1 over here. That's negative 2, that would be negative 3. So we know the y-intercept, we know the c. We can actually find what a is by just manipulating this relationship. A is negative 5. And so the only thing left over is now just to find one single unknown, which is the b. And that could be done by plugging in a single point. I use this one over here. And so 1 goes for the exponent, negative 0.5 goes for the y, and subtracting 2 from both sides, dividing by negative 5, gives me the b. And so here's the model, and do the check that it actually works with another point that's provided. So I kind of went from hardest to middle to easiest here, and I hope that kind of helps you, that there's certain shortcuts you can watch out for, but if you're stuck, work with 3 equations, 3 unknowns, it will get the job done. How does this relate to maybe word problems? So this is going to introduce us to what we'll have to do with word problems. Suppose we want to pass on a message to the whole school population. You tell 5 of your friends with instructions to them that each of them must tell 3 more people the same message. And they must in turn tell every person to tell 3 more, etc. What we're going to do is just create a model for this. When we create an equation, we also need to say let statements. So this assign variables means we need to do let statements. So to do the let statements, the independent variable would be the number of stages. Like every iteration, somebody is telling the next set of people. Let y be number of people who heard the message. And so you're the one who's going to start this off by telling 5 people. So this line represents the 5 people that you relayed the message to. Each of those 5 people tells 3 more. So here we have 1, 2, 3, 1, 2, 3, and so on. So if you were to put this information into a table, this is how it's going to look like. At stage 0, you told 5 people. Stage number 1, each of these 5 people told 3 more, so that's 15. Then these 15 people tell each 3 more, so that's 45. In stage 2, 45 people know the message. So in this table, we can identify the ratios right away. And because the ratios are visible, without you doing differences first, then you know that there is no shift up or down, there is no horizontal asymptote. So the ratio is 3 right away. The change in x, how much it goes up on each stage, is up by 1, up by 1. So that's going to be the period 1. Or so it's going to be in our exponent, the denominator is just going to be 1. And so using this format, okay, we can start filling things in. We have base 3, we have period 1. And to find this c, either substitute 2 points to find a and c, or, I've already kind of said it, but I have a note here. Let's read it. If the ratios are constant right away, without you doing differences, then the horizontal asymptote automatically is 0, and then your y-intercept is going to be your initial value. Here's what I mean. So for us, c is 0, and initial value at the beginning, the y-intercept, that 5 is going to be our a exactly. So why don't we work it out the long way so that you can see how this shortcut, this OR, also works. Okay, so let's do it the long way. Let's say you didn't know this concept, or maybe you just forgot. We have this, we can substitute 2 points. So plugging in the first point, 0, 5, 0 goes for x, 5 goes for the y. We have 2 unknowns, a and c, so we can't continue until we use another point. So plugging in 1 and 15 as the next point, 1 into x, 15 into the y. We have the second equation. Label the equations and show what you're subtracting from what. So 2 minus 1 is what I'm doing. So 15 minus 5 is 10. 3a minus a is 2a, and c minus c is gone. And so that solves it for a to be 5. Once you have a, we can plug it into either equation number 1 or equation number 2 to find the value of c. So here is c equals 0 that I've already mentioned, and a equals 5 that I already said that would be the case. All right, so next. At the end, because we have our let statements, the model is going to be written as a in front, base b, x over 1 plus 0, which you don't have to write over 1 or plus 0. And don't forget that you can check that this equation actually works with our another point in the table to verify that it's okay. Let's keep this information over here, everything I've summarized so far, and try one more word problem. We have a bacteria cell that splits into 2 cells, so one cell becomes 2 cells in about 10 days. Then all the new ones also split into 2 every 10 days, and this pattern continues. We're going to do let statements, so assign variables, and create an equation. So let statements would be the independent variable x would be number of days, and dependent variable y will be number of cells we have at that particular day. So here is a representation. We have a single cell. It splits into 2. So this cell is no longer there. There's these 2 cells over here. Then these 2 each split into 2 again. So if you put that into a table, this is how it's going to look. At the beginning, there's only 1 cell. In 10 days, there's 2 cells. In 20 days, there's 4 cells, and so on. Here, we have a ratio that's visible right away. There's definitely multiplication by 2 as you go down along the y-axis. And there is an addition of plus 10 for changes in x. So the ratio 2 will be our b. The change in x will be the 10 for our p. Okay, so that's the 2 things on the bottom over here that we summarized. Now, because horizontal asymptote, the ratios are constant right away without us doing first the differences, horizontal asymptote is 0, and actually most of the questions you're going to have in 11 university level course will mostly have horizontal asymptote at 0. And then our last part is the y-intercept is actually going to be our initial value. How many cells did we have to add times 0? We had only 1, so that's the 1. So if you actually put everything in together, you're pretty much done. There is no points to substitute knowing this summary over here. And of course, you can check using a point to see if it actually matches.